This fundamental question, what is cold, haunted Robert Boyle, who was born the year after Bacon died. The son of the Earl of Cork, a wealthy nobleman, Boyle used his fortune to build an extensive laboratory. Boyle is famous for his experiments on the nature of air, but he also became the first master of cold. Believing it to be an important but neglected subject, he carried out hundreds of experiments.
He worked through, very systematically, a series of ideas about what cold is. Does it come from the air? Does it come from the absence of light? Is it that there are strange, so-called frigorific, cold-making particles? The dominant view, certainly in Boyle's lifetime, the view that he set out to attack, is that cold is a primordial substance. That when bodies get colder, they're sucking in this primordial cold, and as they get warmer, they expel it. Boyle thought that was wrong, and he did experiments to show that it was wrong.
Boyle was curious about the way water expanded when it turned to ice. He wondered whether the increase in volume was accompanied by an increase in weight. They carefully weighed a barrel of water and took it outside in the snow, leaving it to freeze overnight. Boyle reasoned that if once the water turned to ice, the barrel weighed more, then perhaps cold was a substance after all. But when they reweighed the barrel, they discovered it weighed exactly the same.
So what must be happening, Boyle guessed, was that the particles of water were moving further apart. And that was the expansion, not some substance flowing into the barrel from outside.
Boyle was becoming increasingly convinced that cold was not a substance, but something that was happening to the particles, and began to think back to his earlier experiments with his air pump.
Boyle's idea was that the air trapped in this glass container is springy, it's elastic. As you try and compress it, it resists. Now this is very closely linked in Boyle's program to the way he studies heat and cold. Because his idea was that as substances like the air get warmer, they tend to expand. It's as though the little particles, little springs, out of which he imagined each air particle is made, are gradually unwinding. So they take up more space and they expand. Boyle's conclusion here was that heat is a form of motion of a particular kind, and that as bodies cool down, they move less and less.
Boyle's longest published book was on the cold, yet he found its study troublesome and full of hardships, declaring that he felt like a physician trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glassblowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Because rather than mercury, they used alcohol, which is much lighter, they made thermometers that were sometimes several meters long and were often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally agreed temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
Imagine that you want to make a scale of temperature. What do you do? Well, the obvious thing to do, and this was well understood by instrument makers and experimenters in the 17th and 18th century, is to try and find something in nature which you know always has the same temperature and make that your fixed point. A better strategy even is to find two such phenomena in nature, and then you have a lower fixed point, say something rather cold, and an upper fixed point, something rather warm, and divide the degrees of temperature between into, say, 100 convenient bite-sized chunks. The problem, however, was to define a phenomenon whose temperature you guessed was fixed. So for the lower fixed point, you might choose the temperature of ice just as it's melting. And then there's an almost indefinite range of possible candidates for your upper fixed point. Isaac Newton, for example, worked rather hard on constructing what he called a scale of heat. He, for example, defined the temperature which a human can only just tolerate if they plunge their hand into warm water. It could be the normal human underarm, the temperature of the human blood, the temperature of wax just as it's melting.
The first temperature scale to be widely adopted was devised by Daniel Fahrenheit, an accomplished instrument maker who made thermometers for doctors in Holland. He used a mixture of ice, water and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale into 100 divisions.
The original scale used by Celsius was upside down, so he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
The story begins with the French physicist Guillaume Amonton. He was doing experiments heating and cooling bodies of air to see how they expand and contract.
We're now going to put ice around our bulb and see what happens.
And he was noticing that, well, when you cool a body of air, the volume or the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure, and this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people have actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, for most scientists, the penny had dropped that cold was simply the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion, and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid, that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric, or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements. It's very easy to talk about the quantity of heat and to think of it as a fluid, whereas to talk about the quantity of heat and to think of it as a vibration of the particles of matter, which was the other alternative, that's much more difficult conceptually.
It's a very hard model to refute, Because if you can accept that there's a substance that doesn't have any weight, indeed for Lavoisier, heat, caloric, is an element. It's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
There was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colourful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works, and it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a scientist meant that few dared challenge his ideas. Sadly, this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually guillotined.
The reason he was guillotined was not because of his science, but because he helped run the privatized income tax service of the French state. And there's nothing more unpopular, even in France, than a privatized tax collector. Once he was guillotined, his wife left France and eventually met Rumford when he moved to Western Europe in the early 1800s. Rumford then married her, so he'd married the widow of the man who'd founded the theory that he'd destroyed.
The marriage was short-lived. After a tormented year, Rumford left Madame Lavoisier and devoted the rest of his life to his first love, science. It would be nearly 50 years before his theory of heat and cold was finally accepted. A founder of the Royal Institution, Rumford continued to support the pursuit of science, and it was here that the next major breakthrough in the conquest of cold would occur. Michael Faraday, who later became famous for his work on electricity and magnetism, unwittingly carried out an experiment that would begin the long descent towards absolute zero. He was asked to explore the properties of a newly discovered pungent gas called chlorine. This experiment was potentially explosive, which is perhaps why it was left to Faraday, and perhaps also why Dr. Andrew Shidlow is curious to repeat it today.
We are about to undertake an exceedingly dangerous experiment in which Michael Faraday in 1823 heated this substance here, the hydrate of chlorine, in a sealed tube. Is that sealed?
That's sealed, Andrew.
That's absolutely brilliant.
In the original experiment, Faraday took the sealed tube and heated the end containing the crystals. He put the other end in an ice bath. Soon he noticed yellow chlorine gas being given off.
Because the gas is being produced, pressure's building up. But because this side is so very cold, hopefully what we'll see is some tiny oily droplets of chlorine, liquid chlorine, being produced. It's the pressure which is causing this. Ray, this is where it starts to get dangerous. So if you now take a few steps back.
When Faraday did the experiment, a visitor, Dr. Paris, called in to see what he was up to. Paris pointed out some oily matter in the bottom of the tube. Faraday was curious and decided to break open the tube.
Right, so let's have a look inside here.
The explosion sent shards of glass flying. With the sudden release of pressure, the oily liquid vanished.
And there we are. Is that what happened? Yeah, that's exactly what happened. It popped open, glass flew. And can you detect the strong smell of chlorine?
I can now.
Absolutely. Well, he detected the strong smell of chlorine, and this was a major mystery for him.
Faraday soon realized the increased pressure inside the sealed tube had caused the gas to liquefy. Later, he used the same technique to liquefy ammonia gas. He noticed that on releasing the pressure, the liquid evaporated, triggering a dramatic drop in temperature. He predicted that one day this cooling might be useful.
There is great reason to believe that this cooling technique with ammonia may be successfully employed for the preservation of animal and vegetable substances for the purposes of food.
But Faraday's idea of using ammonia as a refrigerant was ahead of its time. Besides, he had no interest in commercial exploitation.